Okay, so this is chapter 24. Now, chapter 24 is when we're finally getting into organic compounds and hydrocarbons. Now, organic compounds are a really important aspect of chemistry, especially if you're moving into the biochemistry field, right? Or if you're moving on to become like a doctor or get into the health sciences. And that's because what we're going to focus on in this chapter is we're going to look at the molecules that bridge chemistry and biology. And so we're going to look at these four elements: carbon, hydrogen, oxygen, nitrogen, which is some of the most common elements that we find inside of our biochemistry. Now, that doesn't mean that we don't have to worry about other elements. It just means that there are big ones. And so organic chemistry is kind of the study of all compounds that are contained in living, or that contain carbon, whereas biochemistry is the study of chemistry of the living systems. Now, the general characteristic is that most of our carbon is going to make four bonds. If they're all single, then we're going to get the tetrahedral shape, so our sp3 hybridized. If we have a double bond, then we get a trigonal planar shape. If we have a triple bond, then it's linear. And in our organic compounds, the carbon and hydrogen bond is our most common. So these carbons form stable, strong bonds with many elements, including other carbons, hydrogens, oxygens, and nitrogens, and the halogens. What we're going to focus on in this chapter is beginning to identify what we call functional groups. Now, these functional groups, they're not the entire molecule, but they're these subsets or different parts of the molecule that kind of determine how an organic molecule reacts. Now, organic molecules can have none of these functional groups. They can have more than one of these functional groups. But each of these different functional groups give the molecule certain characteristics, certain functions, if you will. And so we're in practice going through some of those functional groups. Some of those functions might help us determine things like solubility. So long non-polar molecules, those are not going to dissolve inside of our polar water. But if we add in a functional group like this at the very end, then it might give it a polar head, and now we've made a soap. So organic molecules such as glucose have polar groups that are soluble in those polar solvents. Other ones might have these long non-polar regions, and then just these small polar regions on one side to kind of act as surfactants, right? And so that could be things like our soaps or detergents, but it can also be things like how we make the lipid bilayer inside of a cell. So these different functional groups act and serve a purpose, and they help dictate the chemistry of our different molecules. Acid-base properties is another one. And so one of the most common ones is our carboxylic acid for our acid-base ones. Another one is our amines for our base side of things. And so these different functional groups bring in these acid and base properties to the larger organic molecule that they're attached to. Now, these next couple of slides help showcase some of these functional groups. And so we're going to walk through and we'll talk about each of them throughout this chapter. So we have things like the alkenes and the alkynes. We have our aromatic compounds. We have alcohols, ethers, thiols, amines. And then we get into the halogens, the aldehydes, the ketones, the carboxylic acids. Ester, amides, and anhydrides. So there's kind of a lot going on there, but it's okay. We're going to get to all of them. So our first one that we're going to talk about is our hydrocarbons. And so hydrocarbons are a special subset of our organic molecules. They contain carbon, but they also only contain hydrogen as well. So our hydrocarbons basically mean that they only contain hydrogen and carbon. Now, they can be further separated into our aliphilic compounds and our aromatic ones. Now, our aromatic ones, they're our conjugated rings. That means that they kind of contain these benzene rings inside, where there are 6 carbons in a row, and then they have alternating double bonds between them. So an example of an aromatic one is this structure right here. You can rewrite that structure to look like a carbon at each of these connecting points. And then you could have a double bond, right? 3 double bonds in there. Now the tricky part about the aromatic is that they can resonate. I'm going to clean up that double bond. And so while we could have our triple bonds looking like this, we could also have them move and look like this. And so to show that it has that resonance, we summarize it with just that circle in the middle. And so that's what an aromatic compound is showing you, is it's really a 6-membered carbon ring with alternating double bonds. And they get their name as aromatic because a lot of those compounds contain an aroma that comes with it. Down here below, our aliphatic ones can be separated further down into our alkanes, our cycloalkanes, alkenes, and alkynes. And so we're going to talk about those coming up. So our hydrocarbons are basically separated into those 4 categories. We have alkanes. Alkanes are all single bonds between the carbons and the hydrogens. We have alkynes. Sorry, this should be alkenes. E-N-E. This is going to be where we have a double bond. And then we have alkynes where we have a triple bond. Now, those double bonds and those triple bonds, they have to be between the carbons because we're only made up of carbons and hydrogens. And so the only triple bond that can be present has to be between the carbons. Same thing for the double bonds because the hydrogens only can ever form one single bond. And then we talked about the aromatic ones down below. And so that's the beginning part of how we can start to separate out our hydrocarbons. So our organic molecules are going to fall into these different classifications, and we use those classifications to talk about the chemistry that they're going to be involved in. Now, there's a lot of different ways to write out formulas for organic chemistry, and they start to get bigger and more complex compared to what we used to have. The most common one is we do our condensed formulas, and so we condense them into groupings. But we also have what we call the structural ones, where we actually show how things are bonded together. So this is a structural formula, and then this one here, or both of these, are condensed. Now, when you first start, I would definitely recommend doing your structural formulas. It will help to see all of your connections. But over time, you're going to want to move towards these condensed ones. Now, the reason why we move towards condensed is because our organic molecules are starting to get very large, and their functional groups, where things are connected and where things are located, start to become very important to the chemistry that's involved. So it's not enough for us to say that we have 4 carbons and 3, 6, 10 hydrogens. That's not enough of what we're looking for. We're looking for, are they all connected in one chain? Are they branched? Are they changed? And so that's why we have to come up with these more detailed ways to write our chemical formulas now as we move into these larger compounds. So you can see that this is our expanded structural formula. We have our condensed ones down here, and we're showing those different connections. Now, whether you have them all straight or bent or kinked, it doesn't really matter. They're all kind of showing you the same situation there. We'd have different isomers if instead of connecting all 4 of those carbons, we had them connected like this. Now that would be a completely different molecule, be an isomer of one of those below. The last one that we're going to get into is our skeletal formulas. Now, skeletal formulas are by far the most commonly used way to draw organic compounds, but they're also the trickiest because it requires you to understand a lot of information that's being left out. So there's a lot of assumptions that get made there, so you want to make sure you understand that. So we're going to practice drawing some of those structural formulas. So our first one that we're going to look at is we're going to look at a molecule of pentane. So pentane has 5 carbon atoms connected to each other and hydrogens with single bonds connected to each. So if we wanted to draw that out, our expanded structural formula would look like this. And we would have to fill in the number of hydrogens that each of those carbons can fit. And so what you notice is that all of the carbons on the ends, they get summarized as CH3. Because they're not connected to another, they're only connected to one other carbon, then they have 3 hydrogens that fit on them. So our end ones are shown as CH3. And then we can condense that next one down into CH2 because it's connected to 2 carbons. CH2, CH2, CH3. And you can even leave out those lines and just write that as CH3, CH2, CH2. And so you know that that's a pentane with all of those attached. Similar to what they've done there. Now our skeletal formula, it's taking that next step. What we're going to do is we're going to use these lines to represent those bonds between those carbons. So you can imagine that each of those connections is a carbon. And since it's hard to tell, if I just draw a straight line, how many different connecting points there are, we're going to alternate going up and down to make that a little bit more clear. So one line is actually 2 carbons. 2 lines is 3 carbons. Now, when they draw a structural formula, what you're assuming that all of those carbons that you can't see is going to make 4 bonds. So if we had drawn the double bond here, then we know there would be a double bond between those 2 carbons. If we drew a triple, we know there'd be a triple. Unless something else is indicated there, like a charge or another bond, then what we're going to do is we're going to assume that each of those carbons form those 4 bonds, and those 4 bonds are going to be connected to hydrogens, unless otherwise shown. So really, this carbon down here at the end, it's not just a carbon, it's a carbon connected to those 3 hydrogens. But we don't show those hydrogens when you do your skeletal formulas. Sometimes we include them when we start to get into the more specific functional groups. So we sometimes include them when we have like our alcohols or our aldehydes. But in general, you can leave them out. They're what we call an implied or an implicit hydrogen. Because when we see those lines, we should know to fill in all of those openings with our hydrogen. The second part, and one of the biggest things that we want to do for this chapter, is we want to figure out our naming. And so we need to work through and come up with the naming of the organic compounds. Now, these follow a different naming set than what we've done with our normal molecules. They follow a similar situation, kind of like our metal coordinate compounds. And so because this is for our organic compounds, we're going to focus a lot on the carbons. The carbons are singled out because of its diversity in the compounds and because of the way it connects with the other ones. So carbon is really the element of life, and that's why our organic compounds there's a whole field of chemistry just focused on that. And so we're going to be talking a lot about them as we go through and do our naming. Now, the first part about going through your naming is you have to find what we call the parent chain. And your parent chain is the longest carbon chain possible. Now, a lot of times that's drawn in the middle, but it's not always that case. So you have to go through and you have to identify which one is your longest one. Once you have done that, then you want to find out all of the substituents. So you want to figure out all of the different groups attached to that parent chain. So we're going to number the carbons of the parent chain, so that way all of our substituents have the lowest numbers. Now, if we have more than one option about which way to number them, the series that is the lowest is the one where it contains the lowest number at the occasion of the first difference. And then if we have more than one option for which one would have the lowest one, then you assign it to whichever one comes in the name first. That's a whole nother set of issues, which are about which substituent to name first. But that's our first part, is we have to figure out the longest chain. We have to figure out the substituents or what we have attached to it. So if we're looking at something like this, our carbon chain here, the longest chain that we have for that first one is going to be 2. We have 1 and 2. Now we don't have anything else attached to those chains. We don't have any other groups. We only have those hydrogens. And so we're not going to have to go on to that next step. We're going to be able to list it with just that. We also don't have to worry about the numbering, since it doesn't really matter since there's no groups attached. Looking at this next one, its longest chain is 3. And the last one, its longest chain is 6. Now, once we know the chain, we've numbered them, we know which substituent is going to come first, we can start to use our prefixes di, tri, and tetra in order to identify how many of those substituents groups. If there's more than one, then you put them in an alphabetical order. But you can ignore the prefixes. The only one that we need to worry about is something that says iso. Now, if we're going through and there's different choices that arise, then there's kind of a set of criteria about how you can choose which of those choices to go with. So when we're trying to select the parent chain, if there's more than one chain where they're all equal length, then you want to go with the one that has the greatest number of side chains. You want to choose the one whose substituents have the lowest numbers. And then from there, you would choose the one that has the greatest number of carbon atoms in the smaller side chain. And then lastly, you have the one with the least branched side chains. So there's a lot of things going on there. We'll walk through some practice problems so that way you can get the hang of it. Now, what I would say with naming organic compounds is it's just like naming molecules. You have to practice, practice, practice in order to get all of them. We're also going to worry about the rings as well. And then it kind of continues on where we have our suffixes that we need to worry about next. So there's a lot going on here. And so these 3 slides is kind of a summary for how we're going to go through and do our naming part. Now, we're going to do a little bit of practice to see that, and then we'll be referencing back to these slides as we go through. So looking at this, we have a chain of 2 carbons, a chain of 3 carbons, and a chain of 6 carbons. And so they want us to come up with our name. And so how we come up with that name is we're going to use certain prefixes to indicate how many carbons we have in a row. So our number of carbons tells us what that base is going to be. So in this case, meth stands for 1. So methane is a 1 carbon. Ethane stands for 2. Prop 3, bute 4, 5 is pent, 6 is hex. And you go all the way on up to dodeca, which is 12. Now, going back to here, we have a chain of 2. So that means that we should start with our F. From there, we need to choose our ending. And this is where we get into our alkanes and our alkenes and our alkynes. So things that only have single bonds are what we call alkanes. Where's this one? And so our alkanes with all single bonds, they end in ane. If you have 1 double bond, you become an alkene, and so you end in ene. And if you have a triple bond, then you become an alkyne, and you end in yne. So if we have 2 carbons attached, all single bonds, then we're going to call it ethane. If we had 2 carbons and they were attached with double bonds, we call it ethene. And if it was 2 carbons connected with a triple bond, we call it ethyne. So in this case, we have just ethane. Get rid of those. The next one here, we have 3 in a row, so that should be prop. That should end in our anes and saw single bond, so propane. This next one, 6 across, we call that hexane. Now we can write them in the skeletal formula, so that would be us drawing out the lines. So ethane should be a line of 2 carbons, so we just draw 1. Propane is 3, so we have 1, 2, 1, 2, 3. And hexane is 6. 1, 2, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. What I would recommend when you draw your structural formulas, always count your carbons at the end. It's very easy to add in either 1 extra or be 1 short, because sometimes we either forget to count the first point where we put our pen down, or we only count the dashes that we make. So you want to go back and want to double check that part. And so then if we want to do heptane, heptane should be 7 carbons in a row. Now we need a little bit more space for that. So 7 carbons in a row should be 1, 2, 3, 4, 5, 6, 7. We need to fill in our hydrogens. And that's how we can get all 7 of our heptanes. So try this one as well. Draw the condensed formula for it. What's its molecular name? Oh, sorry, what is its molecular formula, and then what is its name? So you want to pay attention to the terminology because it is specific. It does give you a clue of what we're looking for. So a condensed one should be CH3, CH2, CH2, CH2. We should have 1, 2, 3, 4, 5, 6. So we have 4, 5. The last one should be CH3. Molecular formula is going to be C6, H3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And then its name is going to be hexane. And so that's our alkanes. Now, our alkanes, remember that their boiling points are going to increase with their size. So the longer the hydrocarbon, or the longer the alkane, the more carbons they have. The more carbons they have, the higher their boiling points and melting points are going to be. And if you want to think about why that is, that's great. And that's because they're all held together by London forces. Because all of our alkanes are nonpolar. Our alkanes can also be further added to in that we can have them in rings, and so we call those cycloalkanes. Now you can have rings with double bonds and triple bonds as well, just kind of like what we did with our aromatics. But one part is that our cyclo part means that we have a ring, and so we add that to the front hand when we name the alkane chain, so that way you know to connect them. So if we have something like propane, propane is 3 carbons. And so if we had just written propane, we would think that it would look like this. But instead, if we say it's cyclopropane, then we know to connect them in the form of a triangle. And so we try to do it in their simplest geometric shape. Now, 3-member rings are unusual to happen. They have a lot of strain that's in them, but we do see a lot of 4, 5, and 6-membered rings inside of our biochemistries. You can have 3. It's not impossible, but it is a little bit of a challenge there. The other part that you'll notice is that when you have a cyclo or a ring in there, it's kind of similar to having a double bond, in that we're going to remove 2 hydrogens in order to make that fit. So propane by itself is C3H8. Cyclopropane is C3H6. It has the same molecular formula as propene, like it would have a double bond. So keep that in mind when you're looking at your structure. So let's try that out. Can you name each of those rings? And so this is the testosterone molecule. So its testosterone one is made up of 1, 2, 3, 4 rings in this case. I don't know why I have 5 written up there. So we're trying to go through and name our different rings. So we need to count the carbons that are inside. So 1, 2, 3, 4, 5, 6. So that should be cyclohexane. Our next one is going to be 1, 2, 3, 4, 5, 6, cyclohexane. Next one, 1, 2, 3, 4, 5, 6, cyclohexane. And then our last one, 1, 2, 3, 4, 5, cyclopentane. And so you just want to keep that in mind as you're going through and naming them. Now, this one actually even has a double bond. And so it wouldn't be an ane, it's going to be an ene. But we'll get into that naming part a little bit later. I just wanted you to see an actual compound where we might see those cyclo ones. And so you should go through and you should try to name these, practice putting those in. And then when you're ready, you can check your answer on the next slide. So our alkanes are all sp3 hybridized, so it's pretty much these tetrahedrals connected to each other. And because they're all single bonds, then they can freely rotate around each other. So they can continue to rotate, and we can keep making those. Now, compounds with the same molecular formula but different connections, remember that those are called structural isomers. And so our structure on isomers looks something like, where do I have my structure? So our structural isomers, we're going to try to draw some of those for pentane. So pentane, our simplest one was connection of 5 of them in a row. Now you might have thought, oh, well, we have cyclopentane. That should be an isomer. And so we might go through and draw it like it's a cyclo. But when we do that, we actually end up being short on our number of hydrogens. This structure up here has 3, 6, 8, 10, 12 hydrogens. This one down here is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that cyclopentane is not a structural isomer. But instead, what we can do is we can take those carbons and instead of attaching them straight across, we can make a side chain. Something that looks like that. Now the difference here is that while we did make this carbon here connect to 3 carbons instead of 2, it allows this one to become an edge carbon, and that's where our extra hydrogen goes. So we still have 12. So that's one option. We can do another one. Right, we can add in another branch to that same one. 5 carbons, 12 hydrogens, so that's the same. So now we have molecules 1, 2, and 3. But now the question is, can you make more than that? Can you make more structural isomers? So move around your carbons, connect them in different ways, see if they really are something new. A lot of times what we happen is we'll notice that we think that we have one, whereas this one is we have 1, 2, 3, 4. So we have a connection coming off the second one. This one we have 1, 2, 3, and so we have 2 connections off the number 2. So we might want to shift it down. We might want to say it's 1, 2, 3, 4, and we'll connect our carbon there. But what you'll notice is that if I were to number from the other side, 1, 2, it ends up being the same one as this structure over here. So it's really not anything new. It's just the same structure, but in reverse. So you really want to practice drawing out those different isomers to really see if it's truly unique, or if it's just one of your other structures, but from a slightly different viewpoint. So this was our propane. This was our branched one. This is our second branched one. And after that, there's no more. So we really do have 3 isomers for this one. So our alkanes are called saturated hydrocarbons. In the same way that they call them saturated fats, it means that it's got the maximum number of hydrogen atoms on each carbon. So everyone's got 3. Or sorry, not 3. Edge ones have 3, interior ones have 2. Unsaturated ones, they're called our alkenes and alkynes, and it's because they don't have the maximum number. They can also be our cycle or rings. The reason why they're called unsaturated is because they have those double bonds, those triple bonds. If we could split those up, we could fit even more hydrogens on there. So if we have 4 single bonds, then we are going to be saturated for our carbons. If we don't, if we have a double bond anywhere in there, then we're going to have an alkene or alkyne or an aromatic. So something like this, our cyclopentane, this is actually saturated because none of those carbons have a double bond on them. They might have 2 single bonds, or 2 single bonds to the carbons and 2 single bonds to hydrogens, but none of them have a double bond. If we add in a double bond like this, now we're going to be a type of alkane, or an alkene, and now we're going to be unsaturated. So remember, alkenes are a double bond, and they're going to be part of our unsaturated ones. Now, alkenes are an interesting part because we use alkenes, and how we add them in is we add them in with the suffix ene. So we add them at the end. So what you want to do first is you find your longest chain of carbons, and you're going to use a number to show where that double bond is. Right now, our longest carbon chain, right, 1, 2, 3, 4, 5, 6, 7, is going to happen between number 3 and number 4. And so we'll use the smaller one first. That's how you know which direction it should go. So how we name this is we name this as 3-heptene. Hep came because our largest chain was 7. Ene is because we have a double bond, and so the 3 is telling us where that double bond is. So that's our base. For this specific example, we still have to name these other 2 groups that we have attached to it. So we have these other carbons, and they're really carbons with 3 hydrogens on them. And so we have to add those names. Now, each of those carbons is just 1 carbon, and so they get the name methyl. Their names really follow the same as our long chain, whatever their starting point is. So for 1, it's meth. For 2, it would be ethyl. 3 would be propyl. We just end them with this YL. That YL is letting you know that it's like an ethane attached to that carbon chain. So it's a methyl. So methyl is a CH3 because that carbon is attached to another carbon. Ethyl is CH3 or CH2 CH3 because one of its hydrogen is gone because it's connecting to our chain. So if we have 2 methyls, then we need to name that dimethyl, and they're connected at carbon 2 and carbon 4. So as we're going through and we're naming and numbering, the numbers are giving us clues about where things are attached. The names are telling us what is attached. And then the prefixes are saying how many of those substituents do we have to attach. Now, our ene number can get moved around there with our suffix, depending on what other suffixes we have attached, but we're going to get to that a little bit later. For this first part, we're just going to practice our naming. So I want you to try this out. This is going to be 2-methyl, 2-pentene. So you want to go ahead and draw out its condensed structural formula and then the skeletal one for it. And then you can do the same thing for 1-methyl, 3-ethyl cyclopentene. So always start with your chain. Our backbone of carbons, we should have 5 of them. And when you first start out, I recommend keeping numbers on them as you first begin. So from here, when we read through this, we know that we have a methyl attached to the number 2 carbon. Well, that's easy. A methyl is 1 carbon with, I guess it's an H3, so we can add those in if we want as well. And so there's our methyl. Our second part is then we can take that part out. We've done that. We've done the pent part. And now we have a 2, and that's going to our ene. So our ene is a double bond. So that means that we need to have a double bond that starts from carbon 2, and we should continue from carbon 2 to carbon 3. So our double bond should go here. And so that's how we know what side it should go on, is it's always going from the lower number to the higher one. Now that we have this backbone all set up, now I can go in and I can worry about my hydrogens in order to make my condensed one. So this one could be my expanded structural formula. This one doesn't need any hydrogens. This one needs 1, 1, 2, 1, 2. So now that we have our expanded structural formula, we're going to do our condensed one. So our condensed one, we should have our CH3, and that's connected to another C, and we have a CH3 up here. And that's connected by a double bond to our CH, CH2, CH3. And so we have our condensed structural formula there. Now when we're ready to do our skeletal one, we basically want to take out those hydrogens. So let's just start with our carbons. And what I would recommend is start with your carbon backbone. So this is carbon 1, 2, 3, 4, 5. And then from carbon 2, so that would be 1, 2, we should have another carbon coming up. And that's our methyl group. And then we should have a double bond coming from 2 to 3. And so now we have our skeletal structure for it. So you can see why it's so much faster and easier to do skeletal structures than it is to do even condensed or even names sometimes. So let's draw the condensed structure and then the skeletal structure for 1-methyl 3-ethyl cyclopentene. So start from your carbon chain, use that as your backbone to build. So we have cyclopentene, so that should be 5. So 1, 2, 3, 4, 5. Now from carbon 1, that's going to be our methyl. From carbon 3, that's going to be an ethyl. So 1, 2, 3. Right, so we would have 2 length carbon there. And then the last one is we need an ene, right? So we need to add in an ene at the end. So we have our methyl, we have our ethyl, and then the last thing we need is we need our double bond. Now, really, I should have written this as 3-ethyl, 1-methyl, cyclopent, 1 ene, to let you know where that double bond is. If it's ever not written, assume it's on the 1. So if this was 1 and this is 3, then we should be going from the 1 to the 2. So it should be on that side for our ene. But I should have specified that. It would have been better. And so that's what you're trying to work with. Alkynes are similar. The difference with alkynes is that instead of ending with ene, you're going to end with "-ine" because you have a triple bond. And so once again, name your longest chain. And then once you have your longest chain, you're going to be able to figure out where your "-ine" fits. So in this one, we start with prop because it's 3 long. We're saying that there's a triple bond between 1 and 2, so that's the 1-propene. And then we have this bromo here. And so if we want to attach a halogen group, we need to say where it's attached to. We're going to give it on to number 3. And so we're going to have that as 3-bromo, 1-propyne. Now, we'll go over the halogens adding compounds a little bit more in depth. It's just for this example, the way that they had found it. They already add the bromo in there. We'll cover that one a little bit later. But we should be able to do it for this one here. This is our methyl and our hexyne. So we should draw it out. So for methyl to hexyne, so hexyne should be 6 long. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I always like to number these when I first off. So 1, 2, 3, 4, 5, 6. Now I'm saying that I have a methyl group coming off of the 4. So that's going to be that one there. We can get rid of that 4 now. And then we have a triple bond coming from the 2 to the 3. So 3. Now sometimes when people draw out structures for triple bonds, what they do is they will draw it as a straight line there, because a triple bond really doesn't have any rotational aspects to it, and it takes on the linear shape there because the geometry around those carbons have to be in a linear structure. So sometimes you see it drawn like that, and the reason why they're doing the triple bond as being linear is because the molecule really is linear at that point. And then for this one, let's go ahead and name our following compound. So we want to look at where our carbons are. So we have carbon 1, carbon 2, carbon 3, carbon 4. So we should be starting with a butane. Now, we know that it can't be an ane because we definitely have a triple bond in there. So we need to end it in -ine. Now we want to go ahead and we want to number them to be our lowest one. So if we start from the left, that becomes 1, 2, 3, 4. So we could have 2 butane. Or if we go from the right to left, we would have 1, 2, 3, 4. So we'd have 2 again. But what's better about numbering from the right to the left and the left to the right is that our chlorine, instead of it being 4 chlorol, if we go from the left, it becomes 1 chlorol. And so we would rather have those two. If everything else is going to be the same, we're going to go with it that way. So go ahead and identify each of these as either an alkane, alkene, or alkyne. So this is alkyne, alkene, alkene, alkene. Now, alkanes can go through different types of reactions. They can go through combustion, which is similar to what we do with our octane inside of your car. They can go through halogenation, where we add in halogens. And so we have several different kinds of reactions that are going on with that. Now, in order for us to add them, for our alkanes, we also have reactions that we can do with our alkenes, right? What we can do is we can get rid of that double or triple bond, and we can saturate it. We can add in hydrogens, or we can add in halides, or in some cases we add in hydrogen halides. So we add an H to one side and the halide to the other. Because what we're doing is we're going to break those pi bonds that are formed and form sigma ones instead. So this is going to be our halogenation, where we're going to take a halogen, add it to that. We basically add in a bromine to either side. We can do it with hydrogen instead. And so what that does is that basically gets rid of our double bond here. And so we have a couple of different options. Now what we can do with alkenes, we can also do with alkynes. It just normally takes more of them because we have to get rid of more and more of those bonds. We'll talk a little bit more about the reactions a little bit later on. Right now, I just want to introduce you to the functional groups so you can feel familiar with that part and the naming, and then when you can worry about memorizing the reaction predictions. So we've been working with those substituents already. So the simplest ones are the addition of alkyl groups. And basically what is happening is we're replacing that hydrogen with some other feature. So alkyl ones are carbon branches. And so how we add those in is we basically replace that ane with that YL. So just like we've been doing with our methyl, our bromo, and our chloro. Halogens are our next one. The halogens are really common, and so that's the group 7A. And all we basically do is we change their ending to oral, and we're adding those in, and they go in based on their alphabetical order. So bromine always comes first, then chlorine, then fluorine, and then iodine. Sorry, I had to remember which one comes next. And so those are our first groups of our functional, those are our first part of our functional groups. We have alkanes, we have alkenes, we have alkynes, we have rings for cyclo, we have halogens, we have substituents, right? Those branch change as well. The next one that we're going to talk about is our alcohols. Now, what's special about an alcohol is it's going to be an oxygen connected to a hydrogen. So this OH group. So similar to that of a base, except it's not going to be an ion. Now, these alcohols are really important because of that hydrogen bond that they bring in. Now, the tricky part about alcohols is that they don't get added into the front necessarily. What they are doing is they can change the suffix. So for our hydrocarbons, instead of ending in ane anymore, now they can end in OL. It becomes a little bit more complicated when it's an alkene and alkyne, but we'll get to that part. So right now that OL part is letting us know that's an alcohol. So isopropanol tells us that it's rubbing alcohol because it ends in that OL part. In the same way that methanol or ethanol are also both alcohols. They end in those groups. So methanol is a really common fuel additive because it burns well. Ethanol is like what you have that's in your alcohol. Right? Isopropanol is what you use for like rubbing alcohol. And so these are important because they're going to give us very polar molecules because of that hydrogen bond. So they have good water solubility and high boiling points. So they're very useful. Cholesterol gets its name because it also has an alcohol group in there as well. And so we see a lot of these different alcohols. So we replace the ane part with the ol part. So instead of being ethane, we become ethanol. Now, if there's more than one, then we can include a prefix to indicate the number. So it'd be a diol or a triol. And then we can show where the chain is or which carbon they're attached to on the chain. We're using the numbers. So our hydroxyl group basically takes precedence over the alkali groups and halogen substitutions in the numbering. So we want to get our alcohol group to kind of have the lowest substituent number when you're going through and numbering them. If we have a double bond and a hydroxyl group, so a double bond and an alcohol present, this en suffix comes right after the chain, and then it's followed by that OL. So what something like that might look like is if we have something that looks kind of like this, and then we have an OH attached. Right, so this is a carbon, carbon, carbon. We would have this as prop. This is going to be 1 ene, 1 ol. And so that's how you can go through and you can name that part. Sorry, that one for this group here should be moved forward. That should be 1 propene, 1 ol. There we go. That makes more sense. And so if there's a choice in the numbering not previously covered, parent chain is numbered to give the lowest number at the first point of difference. So whenever there's a different point, try to minimize that part. So alcohols and phenols, basically the only difference between them is whether or not we attach it to a chain or if we attach it to an aromatic ring. A phenol is the combination of an aromatic ring and that alcohol attached to it. So let's look at naming some of those alcohols. Looking at this one here, we have a chain of 1, 2, 3, 4, 5, 6, 7. So that's going to be our hep part. Looking at our numbers, we have methyl, and then we have, or sorry, we have 2 methyls attached. We have 1 alcohol. And so when we're looking at a numbering, if we go from the bottom up, then our alcohol will become 1, 2, 3, 4, 5. If we go from the left to the right, then it's going to become 3. So that's why we chose this carbon numbering the way it is. And so we can take that hep, we can add in the alcohol ending, and then we can put the 3 there. So we have 3 heptanol. And then from there, we can add in our 2 methyl groups. So we have 2,4 dimethyl 3 heptanol. Now, there's different types of alcohols. We can have what we call a primary alcohol, a secondary alcohol, or a tertiary alcohol. So a primary one means that they're connected to a carbon that's only connected to one other carbon, right? So it's kind of like at the very end. A secondary one means that it's connected to a carbon that's connected to 2 other carbons, right? So like in the branch. And a tertiary one means that our alcohol is connected to a carbon that's connected to 3 other carbons. So it's really branched. So they kind of get their name based on how branched the carbon that they are attached to is, because the alcohol is never going to be attached to anything else besides that carbon. And so this is a primary one. You can see that this alcohol is only attached to this one here. Or sorry, that carbon is only attached to that carbon there. A secondary one is that carbon is connected to 2 others, as well as the alcohol. And then our tertiary, it's connected to 3. So let's try that out. What is the structure of 2-methyl cyclohexanol? Is this a primary, secondary, or tertiary? And then just draw 2,4-dichloryl-1-butanol. And then what is the name of this molecule? So we kind of have a lot going on. Let's do some practice. So 2-methyl cyclohexanol. Hexanol is 6, so 1, 2, 3, 4, 5, 6. We have a methyl, so that should be 1, 2. And then we have an, oh, sorry, I drew a hexanol. I didn't draw a cyclohexanol. Let's start over. So 1, 2, 1, 2, 3, 4, 5. Not sure why this is so hard today. 1, 2, 3, 4, 5, 6. There we go. So we're going to put an alcohol in. This is going to be number 1. And then number 2 is going to be our methyl. And so we have our 2-methyl cyclohexanol. And we know that the alcohol should be on the 1 because it's the dominant one. Now, if we look at this, this carbon is connected to, let me change my color here. This carbon is connected to 2 other carbons. So what type of alcohol is that? Is that primary, secondary, or tertiary? If you said secondary, then you are correct. That is what we're looking for. Our next one that we're going to do is going to be this 2,4-dichloryl-butanol. So butanol finally is going to be straightforward, or not a chain. So 1, 2, 3, 4. We're connecting an alcohol to the number 1 position. We have a chlorine connected to 2. So if this is 1, then this must be 2. And so we should have a chlorine there. We also have one connected to the 4. So 1, 2, 3, 4. There you go. 2,4-dichloryl-1-butanol. Now looking at this, we might be tempted to name this as a benzene ring, right? Or an aromatic compound. But we want to think that this is an aromatic with an alcohol group attached. So that's really a phenol for that compound. So if that's a phenol, then what we want to do is we have to name the chlorines that are attached to it. So our phenol becomes position 1. So our next chlorine becomes 2, 3, 4, 5, 6. So we should have 2,6-dichloryl phenol. So there's some more practice problems for you to do here, right? So you can go through and you can work on naming your different ones. And then on the next slide, I actually have the solutions for you, so that way you guys can practice them. Now I'll click through all of these, so that way in case you don't get them, then you can see them, but you should really practice naming them. It is a little bit tricky as you're going through. Now, there is a hydration for our alkenes. This is when we can add in water, and you can see that we can use that to form our alcohols. And normally what that is you're going to have a water and you're going to add in a strong acid in order to help mirror that. And that's going to be on our secondary alcohols. Next week, what we're going to focus on is something called carbonyls. And so this is a little bit of an intro to that part. A carbonyl group is basically this carbon. So we're going to look at how there is when they're attached to a double bonded oxygen, which is called a ketone. We're going to look at what is when it's attached to a double bonded oxygen and an OH group. That's our carboxylic acid. We'll talk about our esters, where our oxygen's kind of trapped between two of these different long chains. Or an aldehyde, where it's kind of similar to a ketone, but that comes all the way at the end. So it's only bonded to an H on one side instead. And so we'll be looking at that coming up next. So what I would really encourage you to do, start practicing drawing your structural compounds. Start working on your naming, because next week we're going to move forward with even more of those. And so you want to make sure that you're practicing that part. Good luck.